Hello and welcome back to Farms on Farms, where I talk about this nomenclature that we've been talking about for the past two videos, and I go into it a little bit more in terms of the mathematics and the simple arithmetic that can be done with this nomenclature. And I think this is one of the benefits of this nomenclature because you can make very simple calculations about the land area versus the amount of plants you need or the amount of rows you need using this system. Mathematics is very important, especially in the type of farming that I perform, where everything is trying to be timed or spaced in a certain manner within a certain precision rate so that I can have the highest production per time and money invested, and do it in a way that is trying to replicate biology as well, because in nature there are certain mathematical sequences. So if you think back to the scientific revolution of the 17th century, think of people like Galileo, Newton, Kepler. Galileo was a little bit early, and he was the guy who really figured out that, hey, we should actually experiment to try and figure out what we know in terms of the natural world. But Newton and Kepler, they were very into the idea that God had set up these mathematical laws that provided order to a chaotic universe, and that essentially math can describe anything in the natural world. It's not just some abstract concept. It actually applies to reality, and specifically to nature. And because of that truth, mathematics has never been proven to be out of the context of studying nature. Because of that, it also applies to gardening, because if we truly see a garden architecture as building an ecosystem, and we want to replicate it, the garden itself is a replication of the natural world, then we have to include mathematics, because there are things like ideal spacings, where if you plant a plant at a certain width from another plant, it will grow better than if you planted it at another width, because you can get too close where competition arises between the two plants because they're trying to take each other's resources. And then you have times when you plant them too far apart, and that just increases the amount of time you have to go through and harvest these plants because they're spread out more. All that to say, mathematics is important to gardening, and that's why I think it's an advantage for my system to have mathematics in it. So I'm going to pose a problem. How many plants can fit in a row? Okay, so using the garden architecture nomenclature that I discussed in the last video, which is here. So this is okra. O is just my symbol for okra. It could be anything you wanted it to be, though. And we know through the nomenclature that it's spaced out at 6 inches. So there's one plant for every 6 inches, at least theoretically. There was at least one hole made for seeds to be put into every 6 inches. And we have a 10-foot row. So how many plants will go into a 10-foot row? Well, we know they're spaced at 6 inches, and that's kind of the key number for all of this. Because 6 inches is the space in between one plant and the next plant. Because that's the sequence that keeps on repeating, we call that the sequence interval. The sequence interval is just how much space is there, how much linear space is there in between the plant that starts the pattern and the plant that ends the pattern. So here, it's easy. It's just 6 inches. This gets a little bit more complicated when I involve companion planting architectures, which I will in the next video. But right here is very simple. So our sequence interval is 6 inches. So really what we want to know is how many sequence intervals can we put in the row. So again, here's our sequence interval, and here's our row. So what we do is we divide the row length, before I go further, gardens are of course two-dimensional, they're length and width. For the purposes of this video, to make it easier to understand, when I say row, I'm going to say width. And what I don't mean is like how much space are there in between rows. I really mean how wide is your plot. So rows conform to width. The number of rows conform to length. So from here on out, when I say length, I mean number of rows. When I say width, I mean how long the rows are. So you got your plot is 10 foot wide. Then you divide that by the sequence interval, which is 6 inches. Sorry, I know that 6 is a really funky looking 6. And if you're not good at math at all, you can convert this to 10 foot over 0.5 foot, because 6 inches is half of a foot, which that would be 20. Okay? So 10 divided by 1/2 is 20. So that means you're going to need 20 plants to fill up that 10-foot row based on your garden sequence, or the garden architecture that you've laid out for yourself. Now, in all reality, 6 inches is kind of too little space in between each overplant. Really, you want 1 foot. But for the purposes of teaching you how to perform mathematics or arithmetic with this system, it works. So what if we want the inverse of this question? So our first question was how many plants can we fit in a row? How about how wide do we need to make our plot in order to fit a certain number of plants in? So what's our garden architecture? Our garden architecture is BP-18 inches ellipsis. BP stands for bell peppers in my system. Again, it could be the symbol for the actual plant species, could be whatever you want. So we have the architecture is bell peppers spaced every 18 inches. The sequence interval, how long is it from the beginning of the sequence to the end of the sequence, is also 18 inches. And we need to put 50 bell peppers into this plot. So how wide does a plot need to be? Well, we do. This time, because it's the inverse, we're not going to divide, we're going to multiply. So we do 50 times 18. And that is going to yield us, let's see, 40. That's going to yield us 900 inches. Okay. Now what that would be in feet, I can't do the math in my head for that, but it could also be 50 times 1.5 foot, because 18 inches is 1.5 feet. So that would be 25, 50, 0, 5, 7, dot. So that would be 75 foot. Okay? So if you want to figure out how many plants you want in a certain width of a plot, then you divide the plot width by the sequence interval. If you want to figure out how wide your plot should be according to a certain number of plants, and you multiply the number of plants you want by the sequence interval. Okay, so how about length, about plot length? So our next question is going to be how many rows to make in a plot. So here we are adding a little bit more to our garden architecture because we don't only have this garden sequence, we also have the inter-row space right behind it. So remember from the last video, this is kind of how you're spacing your plot, or your plants in your plot, and the dash with a number behind it represents how wide the inter-row space is. So how much space do you have in between the rows? So here you have P spaced at 6 inches with the inter-row space being 1 foot, and you have 100-foot long plot. So how many rows am I going to make? Well, the last time what we were looking at was this number, which wasn't length, it was width, divided by the sequence interval. This time, the sequence interval, because it deals with width, we don't need that in our equation, so we can ignore the sequence interval. It's not dealing in width anyway over here. All we get is length. But this tells you length. This tells you how much space is in between each row. So what we're going to do is we're going to take the length of the plot, 100 feet, and divide that by the inter-row space. So 100 foot divided by 1 foot, that equals 100. So we would have 100 rows of peas. Sounds like a lot to pick. That doesn't sound fun at all. So that's length of the plot, and then we have the inverse. So we divided in the first problem. Now we're going to multiply. So how wide should the plot be for this many rows? Okay, so let's say we have 25 rows of peas spaced at 6 inches, 1 foot apart. So how many rows do we have? Excuse me, that should be how long the plot should be. And here we are multiplying. So last time, let me go ahead and change that, how long it should be. Last time we divided the length by the inter-row space. This time we're multiplying the number of rows, because this literally is the number of times you're replicating this garden sequence, and because there's not multiple rows listed in this garden sequence, which there could be in certain companion plantings, we're just going to multiply it by the inter-row space, which is 1 foot. So 25 times 1 foot equals 25 feet, and that would be how long the plot should be. Okay, so hopefully this is at least somewhat interesting to you guys. This is how I plan out my garden, and I'm going to make one more video for this series in which I actually bring in companion planting architectures. So hopefully that'll be interesting. And I'll follow up this series with my argument. Is basically a thesis for companion efficiency theory, which is something I've been developing in my head for the past 3 years. So with that, I'll see you later. I hope you have a great weekend.